All right, so does Rolle's theorem apply on the interval from 0 to 6? We know that with Rolle's theorem, we're trying to guarantee a slope of 0. Before we get there, though, we have some conditions we have to be able to meet. And one of them is continuity. So the way that we check for continuity is we look in the denominator of the original function and see if the vertical asymptote or the hole is going to cause any issue with our interval. So if we look at the denominator there, we know that this is a location that we can look for vertical asymptote. So we know there's a vertical asymptote when this x plus 2 equals 0, which is x equals -2. Hey, morning. So there's a vertical asymptote at x equals -2. But that location is going to be outside of our interval, right? Our interval is between 0 and 6. So the only break in the graph is safely outside the interval. So we can continue with our problem, the rest of the scenarios. So first condition, we know our function is continuous on the closed interval. Make sure you specify bracket 0 to 6. And then differentiable. Sorry about my key. My key, I didn't specify the distinction, but we need to have the distinction there. Parentheses for differentiable and brackets for continuity. Now, we're trying to guarantee a slope of 0, so there's an additional condition that has to be met, and it's the fact that our endpoints have to give the same y values. Right? That's the only way that we can confirm that our endpoints are going to have the same y value. They're going to be directly across from each other. And if they are directly across from each other, we know that we can therefore draw a horizontal line between them. And that's the only way that we can ensure that there's also a horizontal tangent somewhere between our endpoints. So we're working towards getting that third condition, but first we need to find our endpoints, right? So let's find f of 0. We're going to find f of 6.
Mr. Yang?
Yes.
How did we verify that it's differentiable again?
If it's continuous, it's going to be differentiable.
Okay.
So the problems that I give you are going to be nice and smooth. There are two conditions that is going to be continuous but not differentiable, but we're not going to see those on the quiz. It's like cube root, like fifth root, or sorry, cube root functions, or like absolute value functions. These are the only types on the AP course that you're going to have to deal with in terms of differentiable being an issue.
Mr. Yang?
Yes.
What would happen if the vertical asymptote was in between the interval?
Right. If the asymptote was in the interval, then we say the function is not continuous and Rolle's theorem doesn't apply.
Okay.
So if any of the conditions break down, we can't continue with the theorem. Yeah. Okay, so f of 0. F of 2. Sorry, 6. So these are both 0. These are both the same value. So f of 0 is equal to f of 6. And therefore, all 3 conditions pass. Therefore, we know that for sure there must be a slope of 0, and that's what Rolle's theorem is going to guarantee for us. Okay, I want to make sure that we understand this 0 is not the same thing as this 0. Okay, the reason that we're getting a 0 here is because we're actually finding the slope between the endpoints. We're actually doing slope is change in y over change in x, and that's why we get 0. Okay, so that's the reason. Okay, not because these numbers are 0, but because the slope between the endpoints is 0. So if these were 2 and 2, or 5 and 5, or 6 and 6, the slope is going to be 0, and that's what we can still guarantee is 0. So I want to make sure that we don't just think that whatever number we see here, we're going to translate it here. If these are the same numbers, this is always going to be 0. So we verified that we're good with slope 0. We know that is going to be a guarantee. Now we have to figure out where that slope 0 is going to occur, and that's going to come from the derivative. The derivative is going to help us connect those 2 parts together. The location of the slope 0. So to find f prime, we look at our function, the way that is requiring quotient rule. All right, any questions so far? All right, make sure you take the time to expand all this out. Right? We can't take this shortcut here. This can't happen. Okay, we got to spend the time to expand all this out. So there's my derivative. I have my slope formula. I know I want to figure out where slope is 0, so I'm going to set these equal to each other. Right, when we see this, okay, we're going to be finding a slope 0. So slope 0 is only going to come from the numerator of the derivative. Okay. We're not going to set the denominator equal to 0 separately, because if we do, that's something else, right? That is a place where either slope is undefined or a vertical asymptote or hole. But we're looking specifically for slope 0. So the only place we're going to find a nice smooth slope 0 is going to come from the numerator of the derivative. So that's the only place that we look.
Mr. Yang?
Yeah.
Why is x plus 2 not squared?
Oh, sorry. You're right. Should be squared. Okay. Okay. But for our problem, we're only going to look at the numerator. So we can factor this out. Solve for x, we get -6 and x equals 2. So we have two potential c values. Okay, but how do we know which one to keep?
Two is in the interval.
Yeah, open interval. Okay, so it has to be between the endpoints. If we get a 0 or a 6, that's not good enough either. It has to be between. So -6 is definitely outside. We're guaranteed at least one. So we did get one solution. But -6 is out. So there's one location on this curve where there's a slope 0, and we found it.
Mr. Yang, if
Yeah.
if Rolle's theorem applies, would the slope always be 0 that we always set it equal to?
Yes, if Rolle's theorem applies, we are guaranteed a slope 0. But
Okay.
it's more restrictive, right? So that's why it has to go through this third condition as well. We need those two endpoints to be the same y value before we can jump to this guarantee here. Okay, number 2, mean value theorem. Not as restrictive as Rolle's theorem because we don't have to have a slope 0. But we're still going to find the endpoints. It's just that the chances are that our y values will not be the same, which is fine because we can find the slope, and whatever slope that we get is the slope that we want to guarantee, that we want to set equal to f prime. So Rolle's theorem is basically mean value theorem. It's just a very specific case. Right, it's a very specific instance. It's like it's only a mean value theorem for this specific type, but mean value theorem is more not as restrictive. So again, no, not a polynomial. We may have some continuity issues. Right? Where's our continuity issue here?
The denominator?
Yeah, denominator, right? Set that equal to 0. There's a vertical asymptote at x equals 0. But this is, again, safely outside of our interval. So we know our condition is good to go. First condition passes, second condition passes. No issues with differentiability, rational functions. So here's mean value theorem. We're going to focus our attention on the right side. We're going to find the endpoints, find the y values of our endpoints so that we can find the slope. And then we can turn around and look at the derivative.
Mr. Yang,
Yeah.
will we possibly see a mean value theorem question on the quiz that has to do with product rule? Because I need practice with that.
No, it's only power rule or quotient.
Okay.
Yeah. All right, are we good with this information here? So we have our ordered pairs. Now we're going to find the slope. And this will tell us what slope we want to guarantee. So this tells us that because the slope between the endpoints is a -1 and we have a smooth curve, there must be another location where there's also a slope of -1. But now we can turn our attention, find the derivative, and then we can set them equal to each other and actually find the location of this slope on the graph. Closure rule again. All right, we've gathered all the information that we need. We have our slope, we have our derivative, and now we're going to set them equal to each other. Okay, we have our locations of slope of where there's a slope of -1, but we only can keep what is on the open interval. So -1 is out, right? Only 1 is going to fall inside 1/2 and 2. Morning. All right, any questions? Rolle's theorem, mean value theorem.
Yeah, for the second problem, after we found the -1, how did we get to the quotient rule? Up here, like,
Oh, right here.
yeah.
Oh, so quotient rule, I found that because I'm looking at the original function, and my next step was to get from f of x to f prime.
All right.
So I went through quotient rule.
Okay. And then we set f prime equal to -1.
That's right. Yeah.
All right.
Yeah, we're just kind of following whatever this formula or this theorem is telling us to do. We find the slope, we find the derivative, and then we set them equal to each other. Okay, good. Anything else? All right, number 3, use the second derivative test to classify critical points. So we're going to find max and mins, right? Find the relative max and mins. So here's what we're going to do. We're going to we're going to set f prime equal to 0. And then we're going to take these critical points into f double prime. Okay, so that's basically the direction that we're going to do. Find the critical points from f prime. Rather than creating a slope sign line, we're going to take those values, dump it into f double prime, and then use the results of f double prime to help us conclude whether we have a max or min at that point. So let's set y prime or f prime equal to 0. We'll find f prime first. Okay, so these are now the candidates for max and min. Okay. So now we're going to find f double prime so that we can put that into f double prime. We're going to use concavity to help us decide whether these are max or mins. Okay, so we go through power rule again. Okay, we don't set this equal to 0, right? We're taking these critical points, we're going to put it in there. Okay, there's an issue here, right? Because we can find max and min if we have positive and negative values from second derivatives so that we can conclude whether it's concave up or concave down. But this 0 tells us what? Okay, this is inconclusive. Second derivative test is not going to be a good way to determine what's happening at 0. Maybe it's a max, maybe it's a min, maybe it's neither, but we don't know. Because we need either positive or negative to know whether it's concave up or concave down to make that conclusion. So 0 is not going to be a good test to know what's happening at 0. Okay, so let's find what's happening at 6. All right, 36 is the value that we got. How do you interpret this 36? It's positive, right? That's what's important there. Positive, and we need to be able to know what that means, right? Positive value means what? That our graph is
Concave up.
concave up. Okay, it helps just to kind of give yourself a visual. What does concave up look like? We found slope 0, so if you pair slope 0 and concave up together, the only place that point can live is here. And you can tell that this point must be a relative minimum. All right, questions with number 3?
So if you get 0 for one of the f double primes, just don't even think about it. Just go to the next one.
That's right. Just say that it's inconclusive. We just don't, right? This is not a good test for what's happening at 0. A better place to see what's happening is go to the first derivative test, create a sign line, but you know, if you get a 0, then just say inconclusive and move on. All right, anything else? Okay, back page. All right, we're going to sketch and label here. A couple of things I like to do. I like to plot my points first, then create a slope sign line, then do an initial sketch, and then we can fill in the sketch with the curves from second derivative. So I'd like to do a first draft, then my second derivative sign line, and then my final draft. Okay, so I have some ordered pairs here. I can also put this here as well. This is 1, 2 is another point that's telling us where the point inflection is. So I have 3 things I can put on the graph right now. I know my graph will have to go through those points. Okay, here's my f prime sign line. So first thing I'm looking with f prime is I'm searching for critical points. So if there's any x values that they mention, I'm going to have to put them down. So I have -1 and 2. I see those are the x values that keep appearing. So I want to, if they mention any x value, they're going to go onto my sign line. Okay, so first statement, f prime is greater than 0. We interpret that as slope is positive. Slope is positive to the left of -1 and to the right of 2. Next statement, f prime is less than 0. This is telling us that we have a negative slope between -1 and 2. So I don't know my curves yet, but I can figure, I can at least have some version of the graph, right? I know there's a relative max at -1. I know there's a relative min at 2. I know my graph is going to rise, fall, and rise again. And I just have to go through those points. So rise, fall, and rise again. Okay. It's not perfect, but at least I know the path of my graph. And then once I gather information from my second derivative, I can go back and actually fill in the curves that that it needs. Okay, so I'm down to my last 2 statements. Right. My only critical point is where? 1. just 1, right? Okay, f double prime is less than 0. That tells us we're talking about concave what? Down to the left of 0, sorry, to the left of 1. Second derivative is positive, concave up to the right of 1. So we know that's a point of inflection. They tell us that as well because there's a change in sign from one concavity to the next. So we want everything up to 1 to kind of resemble that concave down shape. And then from 1 forward, it's going to become a concave up shape. So concave down. Followed by concave up. All right, any questions there?
So for the derivative sign, what way you can replace it with x value?
That's right. Yeah, you're only going to place the x values. The less than greater than 0, this is talking about concavity, so these are not x values, so we're not going to place them onto our timeline. Yeah. Okay. Any other questions there with number 4? Okay, let's look at number 5. Find the absolute max, find the absolute min. This is a extreme value theorem problem. We know there's only one condition with EVT. All right, what's the only condition that we need for extreme value theorem? This has to be continuous on the closed interval, right? Yes.
How do you make sure that it is continuous?
Right. The way that we tell for continuity is we look at the denominator and see if there's any x value that can cause the denominator to be 0. So we're going to set the denominator equal to 0 and see if there's any vertical asymptotes or holes or any issues. So we do have a denominator, so we have to do some investigation here. We have to look to see, is there any issues? And if there are any issues, is it going to affect our interval? So the denominator is where we go to look for continuity issues. Okay. So if I try to set x, if I try to solve for x, what's going to happen here? So here's the thing, right? There's a negative inside the square root. Is that a real number? Okay, this is imaginary number. So that tells us that there's no real number that can cause this to be 0. Which means that we're safe, right? Denominator is not going to cause an issue. If you try to locate any x value that can make that 0, it's not going to happen, right? Any number that you square is going to be at least 0 or positive, and that's never going to cause this to be 0. So we looked for it. There's no issues, no continuity issues. We're safe.
Mr. Yang?
Yes.
If the negative is outside the square root, would that change how you would do this problem? If it was like negative square root 4?
Let's say if it was x squared minus 4 in the denominator, then you'll get x squared equals 4, and then plus or minus 2, then that's going to be an issue.
Mr.
Okay,
Yang.
thank you.
Like if I
Wait,
had
so-
x squared minus 4 is equal to 0, now this is okay. This will give us real numbers.
What number would have to be like a number that's bad? Like that wouldn't work.
Okay, let's say our problem was this.
Anything between -4 and 4, right?
That's right. Actually, you know what? It needs to be continuous on the closed interval. So if it lands at the endpoint, it is not good enough. It's going to fail. So if it's between or on the endpoint, it's going to if there's a vertical asymptote either between the endpoints or on the endpoint, it's going to cause the continuity condition to fail.
Okay, so it's got to be outside of -4 and 4.
That's right. It's got to be outside of negative. It's got to be less than -4 and greater than 4 if it's going to pass the continuity condition. If the location of the asymptote is going to pass the continuity condition.
Okay, thank you.
Mm-hmm. Yeah, let's say the problem was this. Let's say the problem was okay. There's a vertical asymptote at 4. But this is going to conflict with our closed interval. So therefore, our function would be not continuous. So if your asymptote is at the endpoint, it's not going to pass. It's going to fail. Okay. All right, so we know our function is continuous on the closed interval. We're safe here. Make sure you state that condition for extreme value theorem. Now, what's our next step? Derivative, because we want to find critical points, right? Critical points. Because we're looking for max and mins, right? We're looking for some candidates. We have 2 candidates. We want to see if there's any additional candidates, and we want to find them from the derivative function. The derivative is going to help us locate either slope 0 or slope undefined, and we'll see if they're inside the interval. Right. If the graph looked like this, right, max and mins are not just going to be endpoints, right? It could be slope 0 or slope undefined, so that's why we go to f prime so that we can locate these points potentially that could be candidates for max and mins, right? Okay, so f prime, quotient rule again. Clean all this up, distribute the numerator through. Combine some like terms. All right, so this is going to be where we search for critical points. Where do we look for critical points? Okay, yeah, numerator and denominator, right? Set both equal to 0. So here we have one critical point at 0. Here, all right, we realized from before that there's a variation of this that didn't work out right. So again, we discover there's no real number here. Okay. Yes.
Why is it a line?
Oh, sorry, that should be prime. Sorry, just f prime. I don't know why I did that. Just first derivative. All right. Is 0 going to be a valid candidate for our problem?
Yes.
Because inside. Good. So just be careful, right? If it's outside the interval, we don't use it. It's possible that you may end up with all these critical points and you don't use any of them because they don't fall inside the interval. So sometimes you may be stuck where you're only testing your endpoints and not any of the critical points. So make sure that your critical point is valid before you just go ahead and use it. So that means we have, yes.
Because it's a closed interval, if x would have equaled 4 or minus 4, would that still be valid?
Right. So what if x was 4?
You wouldn't use it, right?
It'll just be a duplicate, right? So just use it once. Yeah. So if it's 4, then technically you're testing it, but it's also an endpoint, so you're only testing 2 points still.
Okay.
Yeah. If it's a duplicate, then you just test it once. All right. Good. Anything else? So now we know that we have 3 locations where there could be a just now a guaranteed max and mins from one of these 3 locations. So now, what do we do? Original, right? Now we're looking for location, and location is f of x. Back in here. So our decision is going to be based purely on these numbers here. So what's the highest number that we see? 3/5. So that's our absolute max.
Why are we using the 4s?
Why are we using the 4s? Because our candidates for max and mins can either come from critical point or endpoints.
Okay.
Right? If the graph looked like this, right, your max and mins could come from an endpoint, so we have to make sure that we test them because it could end up being the highest point on the graph.
Okay.
Do we only use this for EBT?
Yes, that's right. We only test endpoints for EBT. Right, right. I mean, no. This I just wanted to show you, just kind of convince you that endpoint could be a maximum event. I just want to give an example. This is not what the graph looks like. We do use endpoints for Rolle's theorem and mean value theorem, but the purpose of it is different, right? Mean value theorem, Rolle's theorem, we're using those endpoints to get the ordered pair so we can find the slope. But here we're testing it into the function so that we can actually find the location and compare the location with the other locations. So that's the answer, but if you want to provide more information, you can say, well, max is occurring at x equals 4 and x equals -4. But that's not as important. Okay, absolute minimum value is -1, right? That's the smaller number. That's going to be our absolute minimum. And the less important is the fact that is at x equals 0. Okay, so I'm after the y values. That's what I'm really after.
It is not a because answer.
No, you don't have to because statement. If you go through the steps and show me that you're finding the critical point and that you're testing the endpoint, that's justification enough. Okay. I didn't go through first derivative tests or concavity tests. I felt like those were the easier ones, so I just focused my attention on Rolle's theorem, mean value theorem, second derivative tests, graphing. But any questions with those?
Mr. Yang,
Yes.
when you're like on the test, when you have to use first derivative test, concavity test, and second derivative test, what will the question like ask? Like, how do you know to use it?
Yeah. It'll say, if it says find increase and decrease, relative max, relative min, that means you're going to be using the first derivative. If it's asking for concave up, concave down, point of inflection, you're looking for, using that concavity test to find this, creating a sine line. But second derivative test, I'll specify, I'll say use the second derivative test to find relative max, relative min. But if the problem is saying, find increase, decrease, relative max, relative min, that's going to tell you that you're going to be using first derivative test. You're going to be using slope sine line.
Can you go over on how you do the decreasing and
Yeah.
line?
Mm-hmm. Where's my other word? So here's the steps for first derivative test. We find f prime, we set f prime equal to 0, we solve for x, and then we have our sine line. And now we choose values in each interval to plug in. So I can choose -3, I can choose 0, and I can choose 2, right? And I'm going to plug these numbers into my first derivative function. And all I care about is they going to give me a positive or negative value?
So you just choose any number like below 2.
That's right.
Between -2.
There we go. That's right. And you plug this in. And if it gives you a positive number, you know that interval is positive. You know that this interval is rising, has positive slope.
Right.
If I plug 0 in here, I'm going to get a negative value. So I know that my graph is going to be falling. If I plug 2 in here, I get a positive. I know it's going to be rising. So based off of this, I should be able to answer all my questions about max, min, increase, decrease. And you only have to give me the x values of max and mins.
Does it work as well for the concave?
That's right. So for second derivative function, if I want to find concave up, concave down, I'm going to be making my way to the second derivative function, setting that equal to 0, find those critical points, place them onto my concavity second derivative sine line, choose values in each interval. But careful, right? These are now going to go into my second derivative factored form. And I'm going to be gathering information about positive or negative signs. If I plug -1 in, I'll get negative. But now negative doesn't mean decrease. Now negative means concave down. Negative here is concave down. Positive here is concave up. From this, we should be able to write all of our statements of concave up and concave down and point of inflection. But look at this problem, though. Why is there only a point of inflection at 3 and not at 0? No sign change. Okay? There has to be a sign change in order for us to call it a point of inflection. There has to be a transition from one concavity to the next. So here, it's a candidate, but we realize that it's not going to fulfill the condition that it requires. It needs to change signs. F double prime needs to change signs if we want to call it a point of inflection.
So for every like exercise, like increase and
That's right. Always, yeah. After, but you gotta find your critical points first so that you actually
Yeah,
know
yeah.
what numbers to choose.
And
Yeah.
then plug it to my
Second derivative for
concave and
yeah.
for line I use my
first derivative, right?
equal to 0. Okay.
Right. Another thing that students make mistakes with is once you get done with these test points are not going to show up in your increase decrease. Your increase decrease are just going to be involving your critical points.
Mr. Yang,
Yeah.
what page is that?
This is worksheet 3, page 2
Okay.
from yesterday. All right, you guys need to get ready for your quiz. First period does. All right, good luck, guys.
Mr. Young, last question. For the point of inflection, do you need to state the y value?
Just give me the x value. Just give me the x value.
Alright.
Either
Thank
say
you.
x equals 3, or you can say x. You can say 3 and then leave that space blank for the y value. You don't have to give me the y value.
Okay. Thank you. I'll see you.
All right, see you guys.
Thank you. Have a nice day.
See you guys.